All right, so we're going to do section 7.4, integration of rational functions by partial fractions. So this section is going to be quite long, and again, the whole reason, just like last section, is the setup is what takes forever to do, when it comes to it. But again, this is most of the time one of the only ways we can actually integrate when it comes to it. So pretty much, every situation we're dealing with, it tends to give a different type of strategy to deal with them, right, when it comes to it. And this is pretty much a very good way of breaking down fractions into a much easier way to simplify when it comes to it. Okay. So partial fractions is the process of breaking up the rational function into simpler parts before it was simplified. So what this means is, given a big function, given an actual one like this, what was the original functions we added to get to this, right? Like, what two fractions did we add to get here, or what three fractions do we add to get there? That's essentially what we're going to do. Is, okay, given this, how do we go back to its original 2 or 3 parts itself? Okay. And for that process, it's just it's pretty simple, but again, it's just kind of tedious and just takes a lot of work to deal with. Okay. So the process of reverting the rational is by first factoring the bottom, or just the denominator, completely, like literally factor it completely down after that. Then after that, we're going to do the process of this. So whenever you have just a value with an x at the bottom, and that includes, for example, so you can also have a over ax plus b. Okay. So whenever you have an x, the top number is going to be one single number, just a. However, if you have x to the second power, now you're going to have ax plus b at the top. Now the rule is, usually if you want to try to memorize this, is you always have 1 degree less than you have at the bottom. So notice is 1 degree less, it gives you 0, therefore you have 0 x's. 2 minus 1 is 1, therefore you have degree 1 at the top. So essentially, if we go crazy, if we have something that could not be factorable, like this, or even worse, let's say that's unfactorable, you'll have ax squared plus bx plus c, which is a horrible mess when it comes to that portion. But again, you can kind of tell, that pattern when it comes to, because again, this is degree 3, so therefore you start with degree 2 there. Okay. All right, so now we know, what we're going to be dealing with, how we're going to do this is the interesting part. Okay. So for this case, we're going to do a simple example so you can see how this is going to come into play. Okay. So actually, oh yeah, let me do that. Okay, so what I mean by factor completely is we're going to do a simple little example. And let's suppose we just simply want to factor this. Okay, so the top is already done, and then the inner, you could just do the x method if you guys forgot, right? Little simple ways of factor. Easy 6, 5, therefore it's going to be a 2, 3. Okay, so this is x plus 2, x plus 3. So we have 3 different factors when it comes to it. Therefore, we're going to have 3 different fractions we're going to be adding together. So it's going to be like a over x plus b over x plus 2 plus c over x plus 3. So 3 completely different factors to deal with it. So when it comes to it, so that's how we're going to do these portions here. Now, before we get there, because I know this is a pretty interesting concept, and kind of crazy, right? Is we're going to slowly break it down. So we're going to first start how to actually factor completely, and what they will look like if, at that point, like kind of like the first step or two to deal with it. Okay. So all we're going to do now is just literally factor the bottoms and deal with that portion. Okay. So notice I pretty much did this for you already, right? That was the first example here. So right, it's the same process, right? We just factor out an x, we get this, and just, break it down, we get that. Now how this go about is just like I said earlier, it's going to be a over x, that's your first factor, plus b over x plus 2 plus c over x plus 3. So those 3 fractions add up to give you this. And now the whole goal is figure out what a, b, and c are to make this true. And we know they're simple whole numbers, or it could be fractions, because there's no variable, right? So there's no other variable on top. It's a nice simple numbers we're going to deal with. Again, they could be fractions, but it could be, pretty worse when it comes to it. Okay. So let's keep going. Let's try some more down here. Okay. So again, it's already factored completely, right? So we actually have 4 different factors in this case. 1, 2, 3, and then 4 combined. Okay, so it's factored completely. So every single factor must be associated with this. So we're going to have a over x plus b over 3x minus 2 plus c over x minus 1 plus d over x minus 1 squared. So every possible combination we could have when it comes to it. So as you notice, it can get really, really long depending on what we have at the bottom itself. Okay. So on that process, you can kind of tell what's going to happen here. Okay. So this is x squared. Again, we want to factor completely. Therefore, we're going to have a over x plus bx plus c over x squared plus ex plus d over x squared minus 2. And we keep going. Plus a, b, c, d, e, f, g squared plus, and then finally the last one because it'll be the cubed, h I over x squared minus 2 to the third power. So notice it can be really, really ridiculous at some point when it comes to it. Okay. All right. So I will never give something this outrageous, but I just want to give you the pattern of how, how lengthy this process could be. And again, all this portion is literally the setup when it comes to it. So once we find the letters, the integration actually isn't that difficult. Again, hopefully, right, when it comes to it. Quick little note before we go any further, though, is if the top degree, so the numerator, is larger than the bottom degree, so again, if the top degree is larger than the bottom, before we do this process, we have to do long division to do it. I will usually try to avoid that because I'm pretty, long division is pretty tedious already. So in most cases, you're going to be seeing, the bottom degree is going to be always bigger than the top. Okay. So a common integral we will be using is this one here. So this is, when you want to start it. This is going to be used pretty much extensively in this section because it's very popular. So it's an integral of dx over x squared plus a squared is equal to 1 over a tan inverse of x over a plus c. Okay, so really popular. We're going to be dealing with going to be a lot of examples using this, and pretty much most of the examples in your book as well actually use those as well. So you guys can see how this is going to be applied. Okay, so now that we have this process down, what's an actual question going to look like? Or how do we solve for A, B, C's, and all that fun stuff? Okay, before we go into straight integration practice. Okay, so here's an example we have earlier. Okay, so let's suppose we already did the factor portions, right? And now what we want to do is, okay, I want to add them all up again. Meaning, if I look over here, in order to add fractions, you have to have common denominator, right? So in other words, what would I multiply this to have the common denominator of essentially all of that? Well, I'm missing x plus 1 squared and 3x minus 2. So I would multiply that to the top and vice versa, right, to see what they're checking and applies. That's what we just did here. So in this case, A was missing this, B was missing that, and C was missing that, and when it comes to it. Okay, that's how we get this. Now the question is, how do I get the equations to satisfy or define all the variables themselves? So at this point, we have no choice but to distribute when it comes to it. So here, just foiling out gives you x squared minus 5x plus 4. And distributing this gives you bx squared minus 4bx. And here it gives you cx squared minus cx. All right, and distributing this a finally gives you this. All right, now this whole thing equals on the left-hand side here. Now this is where you got to be careful of. Okay, so before we do anything further, I want to bring all the x squareds together, all the single x's and all the single variables, no x's, and clump them up. So for example, here we have a x squared, we have plus bx squared, plus cx squared there. Okay. All right. Mix all the x's together. So we have negative 5ax, negative 4bx, and then minus cx. So all I'm doing is arranging them, and then finally we just have a single number, 4a, 4a, right? That's it, for no x's. Now how this comes into play is all this here, all the ones with x squareds should add up to give you 5x squared. And all the ones with single x's should add up to give you the one with the single x's. And all the ones with no x's, just the no variables, all add up to the one with no variables there. That is how we're going to set up our system of equations to solve. Now, hopefully, the best case scenario is you can actually solve for one or two, depending on what we already have here. So, essentially what's happening, we're going to have, we know 5 is equal to a plus b plus c, if we just get rid of the x squareds, right? Just think, I say, like, divide them out. We know 3 is equal to negative 5a minus 4b minus c. Again, just following that template here. And we know that negative 16 equals 4a. And would you look at that? We can solve for a right off the bat, right? Just divide it over. So we know a has to equal negative 4 there. So good thing is, right,